Okay, Tome School. Hi, I'm Michael Queppet, and today is my lesson on finding the minimum and maximum values of a function, and it's a calculus lesson. It's part one of a series of lessons I would give on this particular topic. It's part one because in this part, we're not working with all the special cases and all the nitty-gritty nuances of finding the min and max value of certain functions. We're working with nice functions here, and I want the students to understand the general concept. And in later lessons, we would get into sort of things you have to be careful with in special cases. So here it goes. Here's my objectives for the lesson. The students are going to recall the definition of a derivative. What is the derivative of a function? How can you explain it in words? And what does it give you? What does it tell you about this function? Okay, so that's objective 1, objective 2. The third objective is, after the lesson, the students should be able to define what a critical point is. I'm going to define it and mention it many times in the lesson. And not only will they be able to define it, but they're also going to understand the importance of a critical point. Lastly, the students are going to use everything previously in the lesson, so they're going to use their knowledge of derivatives, their knowledge of critical points, and they're going to be able to find the min and max value of functions. And they're going to be able to determine whether it is a min or a max value. That's the last part. So we're going to go over our knowledge on derivatives, we're going to introduce and define critical points, and we're going to talk about them, and then we're going to use all that knowledge to find min and max values of these functions. And this is just an introductory to the topic. Alright, so at this point, students are coming into class. I ask for the homework, which undoubtedly would have dealt with these first two objectives because the students would have already learned that. I would have the students sit in their seats and work quietly for approximately 5 minutes on the following warm-up. Here it is. We're warming up. This is me talking to the students. So let f of x equal negative x squared plus 4. Your job in the warm-up is to sketch the curve of f of x. And when you sketch it, I want you to include just the general shape of it. I want you to include the vertex, so that should give you a little hint about the general shape. And any intercepts on f of x. Y-intercepts, x-intercepts. Remember, f of x and y are the same thing. You can say f of x or you can say y. Okay. Number 2, I want you to find the first derivative of f of x. That is, I want you to find f prime of x. So just find f prime of x. The third thing I want you to do is I want you to find the values of x such that f prime of x is equal to 0. I want you to find the values of x such that f prime of x is equal to 0. So take what you found in step 2, f prime of x, set it equal to 0, and solve for x. Fourth thing I want you to do is, after you've done steps 1 through 3, I want you to draw some kind of conclusion. There's something that you should see, and you'll probably wonder if it's true all the time. So I want you to try to draw some conclusion, and then we're going to talk about it. Okay, guys, get to work, and we'll go over it in about 5 minutes. Okay, so then the students would work, and I would insist on it being silent for at least 4 or 5 minutes, depending on the problem, depending on how I'm, seeing the students are getting it by the looks on their faces. I may or may not let them have a minute or two after this to kind of talk it over with their neighbor or a group member or something and do a little collaboration. Okay, so after they talk about it for not too long, a minute or two, I would jump back into it, and here it goes. Alright guys, so I handed back your homework, and I hope you got through the warm-up problem. The first thing I asked you to do was sketch the graph of f of x. And f of x is written there again. It's negative x squared plus 4x. And what's the shape of that function? So what's the shape? The shape of that is a parabola, right? It's a quadratic function, so the shape is a parabola. And we know that they either go like that or they go like that. And normally we write quadratic functions generally like this: ax squared plus bx plus c, right? And A right here is the lead coefficient. This is the lead coefficient. And when A is negative, it opens down. When A is positive, it opens up. So here, A is equal to -1, so we are opening down. It's going to look like that. That's the general shape. Now, what's the vertex? Well, the vertex of any quadratic that's written in this form, that is, everything's on one side, is given by -b over 2a, comma, f of -b over 2a. And of course, you could complete the square or put it in vertex form and find it a longer way, but this is kind of a shortcut. If you don't understand why this shortcut is a shortcut, see me and we'll go over it. So, what's if we have a is equal to -1, b is equal to 4, and just for, completeness, we have c equal to 0. Because remember, when you don't have a constant term back here, just think of it as plus 0. Okay? So, what is -b over 2a? Well, -b over 2a is -4 over 2 times -1. So, -4 over -2, and that gives you 2. Okay, so for this guy, for -b over 2a, we get 2, right? For f of -b over 2a, that's the same as f of 2, right? And what's f of 2? You got -2 squared plus 4 times 2. So you got -4 plus 8 gives you 4. So the vertex is 2, 4. That's your vertex. Okay, so where are the intercepts? Let's first do x-intercepts, and I'm going to do it in red. So x-intercepts, just let f of x equal 0, and then solve for x, of course, how you always find x-intercepts. And so we're going to have f of x is 0 equals -x squared plus 4x. Now to solve this, I can solve it by factoring. Remember, there's a lot of ways to solve a quadratic equation. One of the least common ways in real life, but most convenient ways in our math books, is solving by factoring. So here we see that each of these summons here has a factor of x in it. So we can factor x out. And what I'm actually going to do is factor -x out in order to get this leading coefficient to be 1. Whenever you can get that leading coefficient to be 1, you should do it because it makes things easier. Anyway, so what values of x on this right-hand side make the right-hand side equal to 0? Well, it's exactly the values of x that make this 0 or make this 0, because that's a product, -x times x minus 4. And if either one of -x or x minus 4 equals 0, the whole side equals 0. So here, obviously, we get the solution of x equals 0, -x equals 0 when x equals 0. And for this guy, all you do is, of course, set this equal to 0 and solve, and you get x equals 4. Okay, so the x-intercepts are 0 and 4. So that's 0, 0, and also 4, 0. Okay, well, turns out when we were finding the x-intercepts, we actually found the y-intercept too, because 0, 0 is also a y-intercept. So the x-intercepts are 0 and 4, and the y-intercept is 0. And now I want to graph this guy. So, let's graph it. Let me get my line tool ready. And first, let's graph those intercepts. So, here's the one intercept, 0, 0. And then the other intercept, we have 4, 0. and we have our vertex at 2 comma 4, so maybe 2 is right here. This is 2 comma 0, and then this is up here. Maybe we'll say that this is 0 comma 4, right? And so this is our vertex right there. And now I'm going to attempt to draw a parabola that opens down like we wanted. Like, this is just a sketch. It might not be pretty. Here it goes. Okay, not the best parabola in the world, but not the worst, you know? So the vertex is right here. This is the vertex right there. And that's what we got. Okay, moving on to step 2 of the warm-up, or part 2 of the warm-up. So I gave you that f of x was negative x squared plus 4x, and then I asked you to find f prime of x. So using our power rule, using our power rule, we can say that this is negative 2 times x to the first, right? We bring this 2 down here. And then this is 4 times 1. We bring the 1 up here, down here, and that goes to x of 0. So we got negative 2x plus 4 times 1 is 4. X to the 0th is 1, but we'll just write it as 4 because 4 times 1 is 4. So there we go. That's f prime of x. Sorry. That's f prime of x. This is the derivative of the function. And on the next page, I'm telling you again that the derivative is what we found. It's negative 2x plus 4. And I ask you for all the values of x that f prime of x is equal to 0. So how do we do that? Well, we set f prime of x equal to 0, and we just solve for x. So, when x equals 2, f prime of x equals 0. Okay, now keep that in mind, and let's look at what's happening at x equals 2 on our graph of the function f. So here we are back at f's graph, and when x equals 2, we get our vertex, we get our maximum value. So, what do you guys think is going on here? What conclusions can you draw? What are you thinking about? What questions are coming up in your mind right now as a possibility for a general truth? What do you got? At this point, I talk to the students, this and that, see what they think, but I'd be trying to go towards the following. Okay. When you find an x such that f prime of x equals 0, that is the x at which f of x is maximized. So that's kind of what we think is true. When we find an x such that f prime of x equals 0, that is the x at which f is maximized. That's the question we're asking. And is it true or not? Well, it's pretty true. So, if we added also minimized here, it would be true. And I'll show you how. But that's the conclusion I wanted you to draw from this. Okay, so let's go into a more general, basic understanding of the building blocks to help us get there. Alright, so wipe the slate clean. Let's start off. First, I want you to recall this definition. I want you to recall the definition, and it's the direct definition of the value of the derivative of some function f of x at a point x equals a. So we're letting f be a function, and we want to know what the value of the derivative of f of x at a point x equals a is. Well, that's the slope of the line tangent to the curve of f of x at x equals a. So remember, the derivative gives you the slope of the tangent line at whatever x value you're talking about. To make it more clear, on the next page, I've drawn a function that you know, sine of x. And we're going to take the derivative of sine of x at different places. So let's just first go over here and we'll take the derivative at pi over 4. We'll take the derivative at 3 pi over 4. We'll take the derivative at 5 pi over 4. And then we'll take the derivative at 7 pi over 4. Okay, so first of all, what is the derivative of f of x? The derivative of sine is cosine. The derivative of sine is cosine, therefore f prime of x is cosine of x. So f prime of pi over 4 is equal to the cosine of pi over 4. So here we are at pi over 4. And what's the tangent line at pi over 4? Let me draw this tangent line for you at pi over 4. It kind of looks like this. And what can we say about it? We can say it's positive, certainly. That's a positive slope on that tangent line. So the slope is positive on that tangent line to f of x at pi over 4. Okay. Now, what's the derivative then at 3 pi over 4? Oh, I didn't actually do this. So cosine of pi over 4 is the square root of 2 over 2. Therefore, the slope of the tangent line of f of x at x equals pi over 4 is square root of 2 over 2. So that's a positive value. All right, let's see what's happening here. Here's what that tangent line looks like. That's not good. Looks maybe something like this. And you can see that the slope of that line is negative. So we would expect the derivative at 3 pi over 4 to be negative. So remember, this is the derivative, and we're plugging in 3 pi over 4 for x. So cosine of 3 pi over 4 is what? It's negative square root of 2 over 2. And if you don't know this, you need to know this because there's a lot of this on the SAT, and it's basic unit circle stuff. So if you need to go back and review your unit circle, please do. This should be common knowledge if you're in calculus. So here we see that the derivative at this point is negative square root of 2 over 2. And that makes sense because this line has a slope that is negative. And we know that the derivative at this point is what? It's the slope of that tangent line at that point. The tangent line to the yellow line, the f of x. Okay, well, now I kind of want to do something funny. What's the slope of the tangent line here at kind of like the vertex of that part of the curve? Well, this is that tangent line. What's the slope of a horizontal line? The slope of a horizontal line is 0. Therefore, the derivative at pi over 2 to f of x, which is sine of x, should be 0. And let's see what it is. So f prime of pi over 2 is equal to the cosine of pi over 2. And that's the x value on the unit circle at pi over 2, and that's 0. So, 0. Good. We can see this would be the same thing. So we can say that f prime of 3 over 2, 3 pi over 2, is equal to 0. And what if we wanted to do 5 pi over 4 or 7 pi over 4? Well, 5 pi over 4 is going to be a negative derivative. So this is going to be negative because the slope of this tangent line is negative, just like up there. And what is it? So f prime of 5 pi over 4 is equal to the cosine of 5 pi over 4, which is equal to, again, negative square root of 2 over 2. Again, if you need to go back and review your unit circle, please do that. Here is the tangent line at 7 pi over 4, and that tangent line looks like it has a positive slope. Therefore, we would expect the derivative to be positive. So, f prime of 7 pi over 4 is equal to the cosine of 7 pi over 4, which is equal to the square root of 2 over 2. And it's the same as this guy was, right? Okay, so what are we seeing here? We're seeing that when the derivative at some point a, okay, all this means x equals a, that means some point. So here, that's some point. We did it for this one, this one, this one. We didn't do it for pi, but we did it for this one, and this one. And we found some things out, okay? So when the derivative at that point was less than 0, we have a negative slope of line tangent to f of x at x equals a. So when we went to x equals a, whatever a was, and we drew the dotted line vertically, and then we took the tangent line, we saw that it was negative when f prime of whatever we were doing was less than 0. So, like, for instance, in this case, when we found out that f prime of 3 pi over 4 was negative, we can see that we have a negative slope on that tangent line at that point. Similarly, when we had f prime of something and it turned out to be positive, we knew it was a positive slope, or we saw that it was a positive slope on that tangent line to the line tangent to f at pi over 4. So when we had this going on, we have a positive slope of line tangent to f of x at whatever x equals a point we're talking about. And then we have this final case, and the final case is when the derivative at some point a is equal to 0. So where did we see that? We saw that here, and we saw that here. When the derivatives equal 0, the slope of the tangent line is 0. Therefore, we have a horizontal tangent line. So the slope of the tan line to f of x at x equals a is 0. And that means you have a horizontal tangent line. Okay, well, let's go back to this. It looks like when you have the horizontal tangent line, so we had the horizontal tangent line right here, and we had it right here. Well, aren't this guy and this guy the maximum and minimum of this function respectively? Yeah, it is. At pi over 2, we have a maximum, and the maximum value is 1. And at 3 pi over 2, we have a maximum value, and that maximum value is negative 1. So, look at this. When we find a value to put in there as the input of the derivative, and we see that that value is equal to 0, we know we have the max and mins of the function because we have these horizontal tangent lines. And what's happening? You see the function increasing over here, right? So the slope of the tangent line is positive. And when the slope of the tangent line is positive, you have an increasing function. Oh, sorry. I accidentally did that. Oops. I accidentally did that in the wrong spot. Hold on 1 second. Excuse me. So when you have a positive slope on the tangent line, you have a increasing function. And when you have a negative slope on the tangent line, like right here or right here, you can see that the function's value is decreasing. The function's value is decreasing during these spots. Whereas when the slope of the tangent line is positive, you can see that the function is increasing. The function is increasing when you have the positive slopes. Okay, so you have the increasing function when the slope of the tangent line is positive, and you have a decreasing function when the slope of the tangent line is negative or less than 0. Now, when it is 0, what's happening? Well, when it is 0, I should do it in a different color. When it is 0, you're going from green positive to pink negative. Green increasing to pink decreasing. Increasing to decreasing. And you have a maximum value when you're increasing, then decreasing. Down here, we have the other guy, the other time where the tangent line's slope is 0 and the derivative equals 0. And we have a decreasing function to an increasing, or a decreasing part of our function to an increasing part of our function. So when you go from decreasing to increasing, you have a minimum. The same way from when you go increasing to decreasing, you have a maximum. So it looks like what our conclusion was is correct. We concluded that if you can take a derivative of a function and find a value of x such that the derivative equals 0, then at that x, the function is minimized or maximized. And look, when we found values such that when we plugged in those values, the derivative equaled 0, that's where we found our min and our max. And the reason that that happens is because the tangent line goes horizontal. And when the tangent line goes horizontal, the tangent line has a slope of 0. And that's when the derivative is equal to 0, because the derivative is the slope of the tangent line at that point. So, let's define something else now. Previously, we just went over what the value of the derivative of a function is. Now, let's talk about this new idea of a critical point. What is a critical point? And we're almost done, actually. A critical point is all those x values such that f prime of x equals 0. And so back on our example here, our critical points here are pi over 2 and 3 pi over 2. Okay? Because those are the values that you can plug into f prime and you can get an output of 0. Okay. So now we know what critical points are. In our warm-up problem, we found that x equals 2 was the value of x that made f prime equal to 0. And it turns out that at 2, we have our maximum. So 2 here is a critical point. And that's because f prime of 2 is equal to 0. So whenever you can find a value for the input that makes the derivative's value output 0, or the output value of the derivative equal to 0, then that is a critical value. So critical values are when you can find an x such that the derivative's output is equal to 0. And the critical points, you guessed it, are the points or the values of x where the minimum and maximum values of the function occur. But how do you know if you have a minimum or maximum value? Well, again, you have to check around it. Is the function increasing or decreasing to the left or right? So here, like I said, so for right here, we had a maximum because we had an increase and then a decrease, right? You're increasing, 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 then decreasing, decreasing, decreasing. Remember, when you increase, f prime is greater than 0, and when you decrease, f prime is less than 0. Because remember, f prime is the slope of the tangent line. This is a positive tangent line. This is a negative tangent line. Okay. Similarly, we found that this was a minimum, and that happened, like I showed you right here, when you have decreasing, then increasing. You have your minimum in between there, right? When you find a function that's decreasing and then it increases, it has to have a minimum value where it stopped decreasing and started increasing, right? And so that is how you tell whether you have a minimum or maximum. So remember, the value of the derivative of f of x at a point x equals a is the slope of the line tangent to the curve f of x at x equals a. And then we know that if we have a negative derivative, then we have a negative slope of the tangent line to f of x at x equals a, and hence we have a decreasing function, right? We have a decreasing function because we can see that when the slope is negative to that tangent line, the function's decreasing. Or the rate of change is negative, so there's a negative change. When you have the positive slope to the tangent line, you can see that the function's increasing. So when you have a positive derivative, you have a positive slope of the tangent line, and you have an increasing function. And then, of course, for when you have that critical value, you get a horizontal tangent line, and you have a minimum or maximum value. And the way you determine whether it's a minimum or maximum value is you have to look at the decreasing or increasing nature of the function surrounding that critical point. Okay, so let's go over an algorithm, and an algorithm is a set of steps to carry out to do a task. Let's find an algorithm for finding a minimum and maximum of a function, or finding minimum and maximum values of a function. There can be more than one, right? So in our sine example, there was at least 2. I only drew a little part of the graph, but in our warm-up, there was only 1, so it varies. But anyway, here's the steps to figure it out. Step 1, you got to find the derivative. So if you're given f of x, the first step is to find the derivative. So find f prime of x. The second step is to find the critical points. So, i.e., find all x such that f prime of x is equal to 0. And you know those values are the mins or the max values. Now, you don't know if they're mins or maxes initially. You might if you had a function that you knew what it looked like we had in the warm-up, but perhaps you don't know what the function looks like. You're at a disadvantage there, and you have to, go about and find it analytically. How do you do that? Well, the way you do that is you have to test points on either side of the critical point to determine whether the critical point corresponds to a min or max value. So we're going to go over explicitly how to do that in this next example. Okay, so what I want you to do in this example is I want you to find the minimum and maximum values of f of x equals negative 2x to the third plus 7x squared minus 3x. Now, unlike our function that we had in the warm-up, this function's not so easy to visualize. It's not so easy to graph. It's cubic, not quadratic. That makes it a little bit more difficult. But suppose that we don't know what this graph looks like. We're at that disadvantage. We're certainly at a big disadvantage, but it's fine. We got it because we have this algorithm to get us through. So what did the algorithm say to do? The algorithm, first step, find the derivative. So step 1, find f prime of x. So if f of x is equal to negative 2x to the third plus 7x squared minus 3x, then f prime of x is equal to negative 6x squared plus 14x minus 3. Okay, so what's going on here? We need to find we need to find the x values such that f prime of x is equal to 0. So remember, step 2, find the critical values. So we want to find all the x values such that x prime of x, or f prime of x, equals 0. So we take f prime of x, which we found right here. So we write f prime of x, so negative 6x squared plus 14x minus 3 equals 0. Okay, so how do you find x in this situation? Well, you have another quadratic. And unfortunately, unlike the last quadratic, we can't factor this quadratic. But what can we always use to find solutions that exist to quadratic equations? We can always use the quadratic formula. And so if a is equal to negative 6, b is equal to 14, and c is equal to negative 3, we have, this is our quadratic formula, it's x equals negative b plus or minus the square root of b squared minus 4ac over 2 times a. Okay? So here the solutions are x equals negative 14 plus or minus the square root of 14 squared, so 14 squared is 196, minus 4 times a, which is negative 6, times c, which is negative 3. All over 2 times a, so that's negative 12, because 2 times negative 6 is negative 12. Okay, so let's simplify that mess, and we get x equals negative 14 plus or minus the square root of 196. You got negative, 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 so it's going to be a negative. 4 times 6 is 24, times 3 is 72, all over negative 12. And so we can kind of simplify that, and it can be x equals 7 over 6, because 14 over 12, and they're both negative, simplifies to 7 over 6, plus or minus the square root of 196 minus 72, so that's going to be 124, square root of 124, and it's going to be like that. Well, anyway, you'd have to put this in a calculator to get approximate results. Otherwise, you're kind of looking at it like, what's the square root of 124? Well, 124 is not a perfect square, so it's not going to come out as an integer. But we know that 10 squared is 100, and we know 11 squared is 121, so it's probably a little over 11. Anyway, point is, you get two solutions here, right? You get an x1 and you get an x2. And x1 turns out to be 0.239, and x2 turns out to be 2.09. Okay? So here are our critical points. Our critical points are 0.239 and 2.09. At these points, we know this is where the min and maxes occur, at these 2 points. We don't know which one, we don't know if x1 is a min, we don't know if x2 is a max, but we know that's where either a min or a maxer occurs at both locations. Okay, so how do we find out if it is a min or a max? So we need to determine whether the critical points x1 and x2 correspond to a min or a max. So this is how we do that. What we basically do is we plot those 2 points, and then we're going to find points around those 2 points. So I'll just say we'll take 0, we'll take 1, and we'll take, let's just take 3, whatever. And again, I'm just putting them in kind of like their place, left or right of the number. It's not precisely placed, and that's fine. So f prime of 0 is equal to what? Well, what's f prime? F prime is this, right? So if x is 0, these two guys are going to cancel out, and we're going to be left with negative 3. So f prime of 0 is negative 3. Negative 3 is less than 0, so you're decreasing over here, right? You're decreasing from here all the way up to here. And now what's going on in between here? Are you increasing or decreasing? The way we're going to figure it out is we're going to let x equal 1 and find f of 1. So f prime of 1 is negative 6 times 1 squared plus 14 times 1 minus 3. So that's going to be negative 6 plus 14 minus 3. So that's going to be 14 minus 9, which is going to give us 5, which is greater than 0. So you're increasing. You're increasing between here and here. You're increasing. And now let's find out what's going on the other side of 2.09, right? So we're going to plug in 3 to f. So, or f prime, sorry. So f prime of 3 is equal to negative 6 times 3 squared plus 14 times 3 minus 3. So negative 6 times 9 is equal to negative 54. And then 14 times 3 is 42. So at this point, we're at negative 12, and then minus 3 is negative 15. And that's less than 0. Therefore, we're decreasing. So just to go over it again, when we plugged in 0, we got f prime of 0 is negative 3, which is less than 0. Negative 3 is less than 0. Therefore, we're decreasing from here all the way to here. Now we want to find out what's going on between 0.239 and 2.09. So we take 1, which is between there, and we see what f prime of 1 is, and we find out that it's 5, and that's greater than 0. Therefore, we are increasing. We're increasing in this interval. We do the same thing for the right of 2.09. We took x equals 3, and we want to know when we plug in 3 to f prime, or the derivative function, what we get. And we got negative 15, which is less than 0. Therefore, since it's less than 0, the slope of the tangent line is negative, and we have a decreasing function. So what do we got here? We got decreasing to increasing to decreasing. Minimum, maximum. Minimum, maximum. So let's just write a little conclusion up here. So min of f of x is, well, what is it? How do we know what it is? Well, we know it occurs at this point, right? So our final step, and I really should add this to our algorithm, step 4, find values of f at the critical points. So all we do is we would plug in 0.2. We plug that in for x, and whatever we get as the output, that's the minimum. And it occurs at 0.239. And the max of f is f of 2.09. So you plug 2.09 in for all these x's, and whatever you get would be the max, and that's how we denote that. I'm not going to go through it right now because I'm not using my calculator. But anyway, we know that 2.09 is the x value at which the maximum occurs, because we knew that it was an increasing function before 2.09, and it was a decreasing function afterwards. So therefore, there had to be a top point at which it stopped increasing and started decreasing. And that's where you get your maximum value. Whew! Okay, so that's a lot of stuff. And this wasn't the easiest lesson to give, but I just wanted to demonstrate my knowledge of the maths. I could have chosen a lot easier of a lesson, but I did not. So at this point, I'd given the lesson, and we've gotten to one example. I would probably give another example if I had time to do so. Or if I did not have time to do so, I'd give a couple problems for the students to do in class, and I could come around and I'd give them maybe 1 or 2 problems that I wanted them to complete before the end of class. And I'd come around and I'd help them, and I'd allow them to work in groups if they showed me that they could handle that privilege. So I'd also give maybe anywhere from 5 to 10 homework problems this night, but no more than that. It wouldn't take them more than, I would say, 45 minutes maximum to finish the homework. But, you know, after I'd done that, or right before I did that actually, I would go back and I would reiterate everything. And this is sort of a hard thing to be doing on a video because I don't have any classroom response. And certainly during the classroom lecture, I would be, you know, interacting with the students and not just kind of talking the whole time. Anyway, I'd retell them what we learned. So today we learned how to find the minimum and maximum values of a function. We reviewed what the definition of a derivative is and the importance of it. And we introduced the idea of critical points, and we figured out what made them important. And of course, the thing that made them important is those are the values of x that the max and the min occur at, because those are the values of x that make the derivative equal to 0, which means that's the slope of the horizontal tangent line at that point, you know. And when you have a horizontal tangent line, you know you're not increasing or decreasing. So you're kind of breaking from increasing or decreasing, and that's why you get the min and max value. So we warmed up with this. We went over some stuff about quadratics. We defined what the derivative of f of x at a point x equals a was, and we went over increasing and decreasing functions. We went over the definition of critical points, and that they're the x values that make the derivative equal to 0. When the derivative equals 0, the slope of the tangent line is 0, so therefore we have a horizontal tangent line, and that's the min or max. The way we find out if a critical point corresponds to a min or a max is we have to see whether the function is increasing or decreasing around it. And we did that by simply finding our critical points, like we did in this last example, and then we found points around it. And remember, just to tell you again, I found these critical points with a calculator because this is way too hard to find without a calculator. Well, all you can do is approximate it, and you approximate it to this, and 124 is not a perfect square, therefore that's why I did it a decimal approximation there. Anyway, that's my lesson, and I hope you enjoyed it. I think that it was quite a lot to fit into one video. I probably would actually space this out a little bit more, but I was a bit ambitious, seeing as I promised you the video by tonight, and I really wanted to do a good job showing that I had good knowledge of the calculus material and that I could convey ideas. I probably would have conveyed about half the ideas in an actual class because, just time constraints and students' attention span. The other thing hard about this video is that I don't know what you're assuming that the students have knowledge of. So I kind of went into functions a little bit more deeply than I would have otherwise if the students had just come off a lesson of increasing and decreasing functions and all that. So I maybe backtracked a little bit more than I should have, but in an actual class that wouldn't be the case because I would be leading the class and I would have a very good bead on where they're at and what they've learned and what I need to go over more in depth and what I did not. I kind of was a little bit too in depth here, I think. But I spent a lot of time on this video. It's about 7:30 right now, and I got out of the interview at about 3, so I've been setting this up and making the video for almost the entire time. I just wanted to put forth a good effort and show what I got. So I hope you really enjoyed it, and again, thank you for giving me the time of day in that interview and taking the time out of your day to do that. That means a lot to me, and I hope that whoever you choose, they do a great job, but I just want you to know that the job sounds really appealing to me, and I'm a teacher of math that really is a fan of rigor and not using calculators and stuff like that. I really want the students to know conceptually what's going on in the math they're learning. So I think that this would be a good fit for me. Anyway, I hope you think so too, and I'm looking forward to hearing your response. Thank you.